Welcome. This is the sixth video in our study of Eratosthenes' sieve as a discrete dynamic system. In this video, we extend the analysis for individual gaps to sequences of gaps known as constellations and address the k-tuple conjecture. Here's where we are with the conjectures about gaps. There's, of course, the twin prime conjecture that the gap g equals 2 occurs infinitely often as a gap between primes. This was extended by Polignac in 1849 to assert that for every even number, a gap of that size occurs infinitely often as a gap between consecutive primes, that there's nothing special about 2. In 1923, Hardy and Littlewood quantified this, and they cited Sylvester from 1871, proposing not only do all even numbers occur as gaps between primes, but the relative frequency of their occurrence has this form of product of p minus 1 over p minus 2 for the odd primes p that divide the gap g. What we have previously shown is that the relative population models in the cycles of gaps support all of these conjectures, that every even number arises and persists in the cycle of gaps corresponding to stages of Eratosthenes' sieve, and that their asymptotic relative population aligns with the estimate given by Sylvester and Hardy and Littlewood. Now let's look at constellations of gaps. A constellation of length j is a sequence of j consecutive gaps. And there's a natural correspondence between constellations of length j, that's the sequence of gaps, and k-tuples with k equal one more than the number of gaps. So you would take a first generator, gamma sub 0, and then add the first gap and get the gamma sub 1, add the second gap, get gamma sub 2, and so there's one more generator than there are gaps. And an instance of a constellation is fixed by identifying that first generator. And all of the remaining numbers, those additional generators, we can obtain just by adding the gaps in order. So the conjectures about gaps get generalized to conjectures about constellations. And so in 1923, there's the k-tuple conjecture that every admissible constellation occurs infinitely often as a constellation of gaps between primes. And this concept of admissibility is to do with divisibility. We'll see that in a minute. Hardy and Littlewood not only assert that every admissible constellation occurs, but they give an estimate of how often it should occur, and note that right-hand factor of p minus nu divided by p minus 1. That factor of p minus nu, we'll see that later. Here's what we're able to show. When we take these models and extend them to models for constellations and the cycles of gaps, they support the k-tuple conjecture. Every admissible constellation of length j arises and persists in the cycle of gaps, and its asymptotic relative population has that factor of prime minus nu. And that nu is the number of residues. We'll look at this product in more detail. What is an admissible constellation in this context? Well, we take a constellation S and consider a prime, P. We define the parameter nu sub P to be the number of distinct residues, modulo P, covered by a k-tuple corresponding to S. So let's unpack this by looking at a couple of examples. The constellation 2-10-2. What is its nu sub 3? So we consider the prime 3. We pick a first generator, gamma sub 0. For simplicity, let's pick 0. We then add 2, get 2, add 10, get 12. 12 is congruent to 0 mod p. We add 2, we get 2 again. So the distinct residues, modulo 3, for this instance are 0 and 2. There are 2 of those. So nu sub 3 is equal to 2 for this constellation. For 5, we again start with the instance, pick the first generator to be equal to 0. Add the 2, get 2, add 10, we get 12. 12 is congruent to 2 mod 5, so again we get 2. We add 2, we get 4. So here are the distinct residues for this instance are 0, 2, and 4. There are 3 of those, so nu sub 5 is equal to 3 for 2, 10, 2. For 7, the span of the constellation is 14, and so again we end up with 3 distinct residues. And for all primes 11 and onward, the 4 candidate primes, those 4 generators, will all have distinct residues. Second quick example, the constellation of length 2, 6, 6. For the prime 3, if we pick our first generator, our instance, to be 0, then we add 6, we get 6. That's congruent to 0 mod 3. We add 6, we get 6. That again is congruent to 0 mod 3. And for this constellation, nu sub 3 is equal to 1. There's a single distinct residue class. And then when we get to 5 and subsequent primes, all of the residues are distinct, and so we end up with nu sub p equal to 3. A constellation is admissible for a prime p if and only if nu sub p is less than p. So whenever nu sub p is less than the prime, the constellation is admissible for that prime. Here's what we're avoiding. Constellations like 2, 2. It's eliminated by the prime 3. It covers all 3 residue classes. The constellation 4, 10, eliminated by the prime 3. It covers all 3 residue classes. And then the repetition of the gap 6 of length 4. So for the prime 3, it only has a single distinct residue class. But for the prime 5, all 5 residues are distinct, and so it's eliminated at the stage prime equal to 5. Inadmissible constellations like these are eliminated by the sieve. For a constellation, there are p minus nu p choices of that first generator modulo p, such that none of the generators are congruent to 0 mod p, so that none of the generators are divisible modulo p, that is a survivable instance of that constellation. And there we see the importance of that parameter nu sub p. A constellation is admissible if and only if it is admissible for every prime p. So an admissible constellation is admissible for every prime. For an admissible constellation, we define this Q to be the product of all primes that divide a span within S. So for the constellation 2, 10, 2, we see that the spans within that constellation are divisible by 2. By 3, I see 12s. It's divisible by 5. That 10 has a span of divisible by 5, and by 7 from end to end. So its Q is 2 times 3 times 5 times 7, 210. The constellation 6, 6 of length 2, its Q is 2 times 3, those 2 primes. The constellation 2, 10, 2, 10, 2, That has spans that are divisible by 2, 3, 5, 7, 11, look for a 22, and 13. From end to end is 26. So there's its Q. This product Q is important in bounding how many primes we have to look at in evaluating nu sub p. So for a constellation S of length j, and for all primes greater than the number of corresponding generators, greater than j plus 1, nu p will only be less than j plus 1 if that prime divides q. Otherwise, for all the rest of the primes, we know that nu sub p is equal to j plus 1. All of the generators will fall into distinct residue classes. So this limits the amount of work we have to do. Eratosthenes' sieve methodically produces all admissible instances of all admissible constellations in the cycle of gaps. Eratosthenes' sieve is an exhaustive factory for admissible constellations in all of their admissible instances. Let's take a look at that recursion. Start with a constellation S, possibly represented by a driving term, and then that initial generator. In step 2 of the recursion, we replicate S at offsets of pk primordial. So the generator gamma sub 0, that becomes replicated at gamma 0 plus pk primordial plus 2k pk primordial, and so on up to nu prime minus 1 times pk primordial. When we look modulo the nu prime, and we consider these nu prime images of this instance of the constellation S, we see that the offsets can be measured in this R sub k, this delta residue, which is pk primordial modulo the nu prime. And so pk primordial grows super exponentially, but instead we can work with this much smaller offset. So when the fusions come in step R3, we don't know which copies the boundary fusions will be in, but the boundary fusions will eliminate nu sub p of these images. And that's the importance of that parameter nu. How many images will be eliminated? If nu is less than the nu prime, then nu prime minus nu of the images will survive. So here's in summary, the cycle of gaps support the k-tuple conjecture. Let S be an admissible constellation of length j. Every instance of S in a cycle of gaps has nu prime minus nu admissible images given by that gamma 0 plus m times p sub k primordial in the new cycle of gaps. So we wrap up here with an example. Consider the constellation of length 3, 2, 10, 2. In the cycle of gaps for 5 primordial, this constellation does not itself occur, but it has the driving term 2, 4, 6, 2. And that initial generator for that driving term is 17. That's our gamma 0. So as we move into the cycle of gaps for 7, then the admissible R mod 7 for that gamma are 1, 3, 4, and 6. And the other 3 will be eliminated by boundary fusions. The delta R here is 2. 5 primordial, which is 30, mod 7 is 2. So let's look at the first image. M is 0, and we have gamma 0 is 17. That's 3 mod 7. 3 is one of the admissible residues, and so that copy survives. When m is 1, we add 5 primordial. The gamma 0 is 47. That's 5 mod 7. Notice the increment. The delta r is 2 from 3 mod 7 to 5 mod 7. In any case, 5 is not on our list of admissible residues, and we see that boundary fusion between the 2 and the 4 after the first 2 is enforced in this instance. For m equals 2, we add 2 times 5 primordial, or 60. Now gamma 0 is 77. That itself is 0 mod 7. So that initial boundary fusion occurs. But in this image, the final boundary fusion also occurs. So that one has 2 boundary fusions. For m equals 3, the residue is 2 mod 7. That is not an admissible residue. That other boundary fusion has occurred in this copy. When m is 4, the 5th copy, the residue is 4 mod 7. That is in our list of admissible residues. That copy survives. 5, that copy survives, 6 mod 7. And when m is 6, the residue for gamma 0 is 1, which is in our list of admissible residues mod 7 for this constellation. Note that here the interior fusion between the 4 and the 6 is enforced in this copy. And so we get a copy of the constellation itself, 2, 10, 2. Path ahead, we are going to take the work we did in getting relative population models for gaps in the cycle of gaps. We're going to extend those to constellations of length j, and we're going to check the survivability conditions and in the interval of survival and look for that consistency, just as we did before. I do want to note that this concept of primordial coordinates, starting with a gamma 0 for a constellation and tracking the images through stages of the sieve by developing these coordinates m, it's a very compact way of tracking images of a constellation through very large numbers. Not sure if we'll get returned to that in this series or not. Thank you.